Well, here I am. Thank you for the introduction. And given that I am early, I should say those prizes you give out, I don't know everybody on the list, obviously, but the people that I do know on the list, you do kind of think, yeah, you're worthy of a prize. I mean, the system might be painful or whatever you're saying, but it's doing the right thing. Um, so so which proofs need computer assistance? Right. So I'm slightly off. I expect it to be slightly off. Let me There we go. So thank you very much for the invitation, and move my cursor out of the way, and let's make the mouse because we tested it. There we go. So what am I going to talk about? I'm going to talk about proof. I'm going to talk about proofs. I'll give some examples of proofs. I'll talk about sort of historical proofs and modern proofs. Hey. I'll talk about how the nature of proofs has changed over time as we've got better at them and as we've got better tools to help us with them. I'll talk about new ways that modern technology is interacting with the idea of a proof. But yeah, there'll be no, I was told to give a general mathematical audience talk. So it's one thing you learn when you're formalizing mathematics is that somehow we use words in ambiguous ways. So what I mean, I'm really going to give some examples of statements of theorems, and I won't give the proofs of the theorem. So when I say a proof, I'll say a theorem for which humanity knows a proof is what I really mean. Okay, so where do proofs start? Well, thousands of years ago, right? The concept of a mathematical theorem and proof, it goes back to, at the very least, Euclid. So Euclid Book 1, the last Book 1 theorem in Euclid Book 1 is his exposition of the Pythagorean theorem, which of course historically goes back even earlier. And in fact, the last theorem in Book 1 is the converse to Pythagoras' theorem. Like if a squared add b squared is c squared, then it was a right-angled triangle. But the last Book 1 theorem is the Pythagorean theorem, and that fits nicely into Book 1. And then there's another very famous proof in Euclid is the infinitude of primes, which is in Book 9. So it's worth. I spent some time. I'd never read Euclid, but my understanding is that sort of 200 years ago, everyone who was anyone who had read Euclid. This was a very popular book. So I've been reading Euclid recently, and in fact, in Book 9, Euclid actually proves that there are 4 primes. This is when you read it. He says, "Well, imagine there were only 3 primes, then multiply them together and add 1." And he's sort of, but this is some sort of standard. This is the way that things were presented because they didn't even have notation for imagine there are only n primes. So yeah, Euclid proved that there were at least 4 primes, and that was in, and again, that's 2,500 years ago. And when you actually read the proofs they're logical derivations from the axioms, but the axioms are completely disjoint. It's sort of interesting to observe. So Book 1 is all about geometry, and he writes down the axioms for geometry. Things like all right angles are equal, and these slightly obscure. Equals added to equals are equal. There's no numbers in Euclid. You might think that Pythagoras' theorem says a squared add b squared is c squared, but there's no. It's literally physical drawings of squares, and it says this square and this square equal this square. And he gives a careful definition of what he means by equal. And it means that you can chop one of these things up into finitely many pieces and rearrange it to the other thing. So for Euclid, a square and a circle could never be equal. Yeah. Because you can't do the chopping. So like there's no pi. Archimedes is full of pi because Archimedes was somehow a physicist. It was pouring water between different containers, but there's no pi in Euclid, probably for that reason. And the proof of the infinitude primes, uses basic axioms for the natural numbers. So there are 2 proofs, but in some sense they're proofs living in disjoint places. But the one thing they have in common is they're both quite short. And because that was what things looked like 2,500 years ago, but proofs didn't stay that short forever. All right, that's kind of the issue that I want to talk about. So yeah, and let's fast forward 2,000 years to Galois. So this isn't going to be a crash course in algebra, but in the 1830s, one interpretation of the facts is one rather pithy interpretation. Galois invented group theory. That's one way of explaining what's going on. And I guess historically, but this is 40 years before Cantor came along and said, let X be a set, right? So things were more concrete in those days. And so these Galois groups that Galois invented, they were automorphism groups. So they were objects that, the complex numbers existed and sort of subsets of the complex numbers existed and maps between those subsets existed. And so you could make things, out of this concrete data. We're still a few years away or a few decades away from, let V be a vector space and let's not really say what the elements of V are. But so a lot of what Galois was doing was somehow looking at things which were subsets of the complex numbers. But he realized that when you started looking at maps between these things or bijections or whatever isomorphisms between these things, then you would run into symmetries. So what Galois was doing was the setup that he would have two fields. Okay? So fields, addition, subtraction, multiplication, division, except by zero. So he's got two fields. One is a smaller field that's contained in a bigger field. And then this fundamental concept, he wanted to look at the isomorphisms from the bigger field to itself, so maps from L to L that preserve addition and multiplication. But these isomorphisms, they not only must they send K to K, but they must send an element of K to itself, right? They can move L around, but they have to keep K fixed. And I've lectured Galois theory many times at Imperial, and the first example I always give right at the beginning of the first lecture is Gal C over R. So the real numbers are a field and the complex numbers are a bigger field. And you ask yourself the question, I want to find a map from the complex numbers to itself that preserves addition and multiplication, but is the identity on every real number. And so in particular, you can check that already that implies that this thing is a linear map, an R linear map on a two-dimensional real vector space. So the big question, of course, is where does I go, right? Because we know where one goes to one. And now where does I go? And I is going to go to some, we're not sure yet, I is going to go to some complex number, but if I goes to X, then I squared will go to X squared, and I squared is -1, and -1's real. And so the real number has to be, -1 goes to itself. So I goes to X, I squared is -1, so X squared is -1. And there are two possible choices. X is either I, in which case this maps the identity, or X is -I. And so now you've got a map that's the identity on the reals and says I to -I, and that's complex conjugation. So this Galois group got size 2. And in fact, the fundamental theorem of Galois theory says that it's no coincidence that the size of this Galois group is also equal to the dimension the complexes over the reals. But this isn't a Galois theory lecture. So I just wanted to, I'm going to talk about Galois groups because they're going to be examples of groups, but it doesn't really even matter if you can't keep the definition in your head. This is just like, you get given some algebraic data, you get a group. And Galois, as I say, you thought about these groups in quite a concrete way. Typically, you would have a small field, and then you would have a big field that was generated by the small field, and then the roots of a polynomial. And you would keep track of, you would work out what was happening to the big field by looking where the roots went. So like x squared plus 1 is a polynomial with real coefficients, but complex roots. And you keep track of where the complex roots are going. And so you can understand these Galois groups as permutation groups. The two roots of this are plus or minus I, and the identity is leaving them fixed, and complex conjugation is switching them around. So they're sort of simultaneously abstract automorphisms of fields and also permutations of finite sets. And as I say, so now Galois' name is embedded in algebra. We say, if you've got a small field and a big field, you say the big field is Galois over the small field. If you can make the big field by starting with the small field and then throwing in all the roots of a polynomial with coefficients in the small field. So there you go. So there's a crash course in Galois theory. So historically, this was how groups were born. But Galois was interested in things like insolvability of the quintic. So you don't really want to work with things like the complex numbers where quintics are already factorizing. You want to work with smaller fields. So typically, he was thinking about Galois groups of number fields or finite fields. So what's a number field? It's just a field that contains the rationals. So you can think of it as a subset of the complex numbers. It contains the rationals. It's closed under addition, subtraction, multiplication, and division. But it's finite dimensional. That's what separates the number fields from the general subfields of C. So Q or Q of I, or you take a cube root of 37. This is a three-dimensional number field here. And then a non-example would be the reals, because it's too big. The reals are uncountable. So all these number fields are countable. So that's what Galois had. He had these abstract examples of field. He didn't have to invent abstract field theory, because everything for him is a subset of the complex numbers. But you can still think about how these things move around. So there you go. So he's looking at Galois groups of number fields, and he's got this new concept of a group, and what are the easiest groups to understand. And it becomes clear quite early on that the easiest groups to understand are the commutative groups. Every finite abelian group is a product of cyclic groups, and there's your classification theorem, and that might even be proved in an undergraduate curriculum. But trying to understand a general finite group, you've got like the classification of finite simple groups, which is a complex thing. So without a doubt, abelian groups are going to be in trouble, because I'm going to need a drink. Give them some water. And somebody magically get me a thank you. Sorry, sir. So the easiest groups to understand are commutative groups. And so in this context, already a very natural question is, well, we've got these groups coming out of number theory, coming out of number fields, and you're given a fixed number field downstairs. How do you get fields upstairs? How do you get bigger fields such that the group is abelian? Right? This is a question that drops out shortly after the definitions appear, if you look at the way definitions appeared historically. Thank you, Mignon. And
sorry, sparkling reports.
And the reason that this question is quite subtle, though, is that thank you very much. The reason that this question is subtle is because what happens if you just take a random polynomial and you look at its roots randomly? These just generate some independent collection of complex numbers, and typically you can just permute them around any way you like. Most Galois groups are symmetric groups, and of course symmetric groups tend not to be commutative the moment your polynomial has degree 3 or more. And so this question, as I say, I'm going to argue that it sort of comes out rather naturally. But also, one thing I want to explain is it turns out to be an incredibly deep and complex and profound question, rather surprisingly. And one that people started thinking about somehow almost immediately, and it took maybe sort of 60 or 70 years to be solved. So what's the simplest number field? It's the smallest number field, the rational numbers. And so the basic example of this question, we're going to consider fields containing the rational numbers and ask if their automorphism groups are abelian. So here's some examples. This already indicates something else. Kind of you put yourself back in the world of 1830. This field Q root 2, which is numbers of the form a plus b times square root of 2 with a and b rational numbers, right? So this is two-dimensional over the rationals. And the Galois group of this object has got size 2 because you can either have the identity or you can send a plus b root 2 to a minus b root 2, because root 2 has to go to somewhere, but its square had better be 2. And so a plus b root 2 goes to a minus b root 2. And if you think about q root 2 as a subset of the real numbers, then this map here is just completely discontinuous, right? This is a really big square root of 2 moves from being positive to being negative, but you can get rational numbers arbitrarily close to square root of 2, they're being a, so they wouldn't move at all. So this function is sort of discontinuous everywhere. And you've got to remember that discontinuous functions were not really a thing in the 1830s, right? You learn like the Heaviside step function. This is like 0 for x negative and 1 for x positive. And And like, it's not really a big deal, but actually it must have been a big deal. And like, somebody, this is named after somebody. So clearly, people must have thought there was. I mean, the Heaviside was, he was a physicist, right? He was interested in electromagnetism. He's interested in what happens when you switch the switch, and it goes like that. But he wants to model that using mathematics, but he's got to come up, with this crazy function that's identically 0 and then jumps and is identically 1. And people like Euler were not really considering those kinds of functions. Euler, a function, basically always had a power series expansion. So some revolutionary things that we just don't think twice about. I think about Q root 2 as being, there's a rational part and there's a root 2 part, and I draw it as a two-dimensional object, and root 2 is just, even it's not on the real line, it's sort of floating above or the rational line. But mysterious things are happening here. So there's an example of a field that has a abelian Galois group over Q. And more generally, of course, it's nothing to do with 2, right? You can take the square root of any non-square, Q root D. So there's infinitely many examples of fields that are Galois over Q with a Galois group. But here's a much bigger example. So here are E and pi, which are real numbers which are nothing to do with algebraic number theory. But you put them together and you can make a complex number, e to the 2 pi I over n. This is an nth root of unity. And then we can look at the smallest field containing the rationals and e to the 2 pi I over n. And so now we've got a bigger field called the cyclotomic field. And it turns out, again, the automorphism group of this field is what's going on here is that how do you make this field? You start with the rationals and then you throw in all the roots of x to the n minus 1. And in stark contrast to a random polynomial where the roots might be linearly, completely algebraically unrelated to each other, here, all of the, like, if I have one of these roots, I can generate all of the other roots by just multiplying it by myself, right? So, there's some mysterious symmetry that this polynomial has that a general polynomial doesn't. And this is manifesting itself in this field here, being Galois over cube, and the Galois group is abelian. So I think that's the most mathsy I'm going to get. So now I'll tell you some theorems. So in 1853, Kronecker said he'd figured it out, and the way it worked was that any number field, if it was Galois over Q and the Galois group was abelian, then it had to be a subfield of a cyclotomic field. This was Kronecker's theorem in 1853, and so an example I showed you, Q root 2 was an example, but a pleasant exercise is if you draw the 8th root of unity in the complex plane, and then you draw, it's 8 powers, so you can add together that one, and you'll get to square root of 2. So you can make square root of 2 by adding together roots of unity, and more generally, even using Gauss sums, you can check that you can make square root of d by adding together some 4d roots of unity. But Kronecker's proof was incomplete. There were problems for extensions of degree a power of 2, and it wasn't until 33 years later when Weber picked up Kronecker's proof, except Weber's proof was incorrect. And this theorem is now known as the Kronecker-Weber theorem. And the first complete proof was given by Hilbert. So 10 years after Weber. So it's called the Kronecker-Weber theorem, even though neither of them proved it. But that's sort of the way mathematics works. So that's great. That's done. And now, in fact, we know better. This is when I was doing CASM, as it was referred to earlier. When I was doing part 3, I read about this in Marcus's book on number fields, and it's presented as a series of exercises. So it's the kind of thing you could imagine you're giving a 1 lecture long proof in an MSc level number field. The reason that this is typically not lectured is you have to know Galois theory and algebraic number theory, and certainly at Imperial, like the Galois theory class, you can't assume the students have done algebraic number theory. In the algebraic number theory class, you can't assume they've done Galois theory. So you have to sort of wait until you're, you have to be 1 level above that. So there you go. So there's Galois and some groups, but actually Galois group, although we credit Galois with inventing group theory, 30 years before that, Gauss had accidentally invented group theory without really making a big deal about it. Because what Gauss was doing was he was studying binary quadratic forms. He got really into binary quadratic forms at some point. And he was playing with binary quadratic forms, and he managed to find a way of multiplying two binary quadratic forms. So he would fix a negative integer, negative d, and then he would look at integral binary, so things of the form ax squared add bxy add cy squared. And the rule was that they all had to have the same discriminant. B squared minus 4ac had to be the same. And so you get infinitely many integral binary quadratic forms with a fixed discriminant. But then he found some notion of equivalence. He didn't have the language of equivalence relation, but he found some notion of what it meant for two binary quadratic forms to be equivalent. So basically, you change your basis. One of them becomes the other when you change basis by an element of SL2Z. And so he had these concepts of equivalence. Well, he just called them classes of integral binary quadratic forms, and he figured out how to multiply them together, right? And it's not at all clear. Like if you multiplied x squared plus y squared by x squared plus y squared in the naive way, you'll get something of degree 4, right? But the Gauss figured out how to multiply x squared plus y, or to compose x squared plus y squared with x squared plus y squared, and you get x squared plus y squared again. Because for d is negative 4, this group has got order 1. All the binary quadratic forms are equivalent. They're all equivalent to this. And x squared plus y squared composed with x squared plus y squared is x squared plus y squared here. So I won't tell you what the group law is, but he figured out how to multiply these binary quadratic forms, all these classes of binary quadratic forms together. And he proves in his disquisitiones, he proves that the group is finite, and he proves all the axioms for a commutative group without ever saying, oh, this is because he just somehow wasn't thinking about discovering new algebraic objects, but he proved all the axioms for a group. They're all in there. So in some sense, he's made an abstract group without even knowing what a group is. And so because Gauss was constantly talking about classes, these are now known as class groups, because that was they were really the elements for equivalence, well, what we now call equivalence classes. So these groups are now known as class groups. And by the 1870s, Dedekind, who now had a much more abstract concept of abstract algebraic machinery, he was quite happy with doing algebra in the integers of a number field. He reinterpreted Gauss's work as actually being a way you could start with this number field here, this imaginary quadratic field q root minus d, and then you take its ring of integers and you take ideals, and the norm form of this ideal is this binary quadratic form, and he managed to figure out what Gauss was doing and also generalize it to any number field. And by this point in the 1870s, we were given a number field K, we can make a mysterious finite group. And because Gausses were called class groups, these were also called class. And this group is, as I say, the class group of the rationals is 1 because the integers, every ideal is principal in the integers. And in general, you make these class groups where you take ideals, but then you quotient out by principal ideals. And you get a class group. So there we go. So now we've got this thing. You start with a number field and you get a finite group, and it's called a class group. And then we go back to Hilbert, who had really the first profound, a lot of these things are profound, but Hilbert really saw something that nobody else had seen before. That these historically, the first 2 examples of groups that had appeared, right? These class groups of Gauss and these Galois groups of Galois, historically 2 very early examples of groups. Hilbert realized that actually class groups were a special case of Galois groups. It was a really extraordinary insight. That you're given a field K, and now this has some class group that in special cases Gauss had made. And Hilbert realized that this class group should be equal to a Galois group. There should be some mysterious field that's bigger than K somehow, and the Galois group of this bigger field should be this class group. So this is not the kind of thing where you can just follow your nose and write it. If you're good at algebra, you can't just sit and write this thing down. Right? And one reason you can't is because the class group of K, you make it internally. You look at the arithmetic of K, you look at the integers and the ideals, and you make it internally. Whereas the Galois group, this is some external thing. You start with something that's bigger than K and you move it around. So, and K remains stationary. So that was because these groups were class groups, this field H became known as a class field, the Hilbert class field of K. And so that's where the nomenclature came from. And the existence of this Hilbert class field was proved 20 years later by Takagi in basically the final paper, the paper that wrapped up what is now known as class field theory. So understanding all of the abelian extensions of a given number field. So this was, as I said, this is now just over 100 years old, this theory, class field theory. And this was really a triumph of early 20th century mathematics and the culmination of a vast amount of work, over 100 years of work in some sense. So there's class field theory that explains, if you start with a number field K, it tells us all about the extensions of K that have abelian Galois groups. Okay, and at the time, the proofs are massive, right? So in case the rationals, we know what these fields L are. They're all subfields of cyclotomic fields. But Galois theory, class field theory for general K doesn't tell us, it tells us what the groups are, but not what the fields are. The fields are sort of a mystery. And Hilbert already saw this 100 years ago. Hilbert's 12th problem, he said, okay, we know what the answer is for the rationals, is subfields of cyclotomic fields, and there's this transcendental function, there's e to the I theta involved here. Maybe, and for imaginary, Gauss's case, imaginary quadratic fields, we'd figured out how to generate Hilbert's class field by using this J function that came up in modular forms. And so Hilbert asked what the general question, what the general story was, given a random number field, how do you make these bigger fields with these mysteriously abelian Galois groups? And nobody knows. There's some sort of preliminary results for totally real and CM fields by Shimura in the 1960s, but there's really still no 0% of number fields are totally real or stiff. So this problem is still wide open. Very wide open. So it's quite funny. So we understand the groups, but not the fields. We can work out the automorphisms of L without knowing what L is. Anyway. So there you go. So there's class field theory, and at the time this is probably a candidate for like biggest known proof. So of course, but then what happens historically is that things get generalized and things get simplified, and we invent more abstractions, and things get easier and easier. So there were theoretical developments, for example, Noether really explained how we should be doing algebra, and methods from topology. Number theory is like a parasite, right? You get ideas from other areas of mathematics, and number theory is like, oh yeah, I'll have that. So cohomology, which is originally used to try and understand geometry, group cohomology can be used to give far more conceptual statements about what was going on in class field theory. So things were generalized and simplified and generalized and simplified. And by the 1960s, it was great. We got it down to 360 pages. Still a very big, I mean, maybe that's a bit unfair, but like the book Cassels and Fröhlich, the book I learned class field theory from, you're 200 pages into that book and you still haven't proved the main theorems. Very. So when I had my midlife crisis in 2017, I got very worried about mathematics. I gave a talk. My life has got quite weird. I gave a talk in a philosophy department in the Rive Gauche in Paris, and a philosopher of mathematics came up to me, and I was whinging about like proofs were big and might not be right, and this paranoid worries I was having at the time. And this philosopher said, "It's okay. Like that's the nature of research. At the boundary of research mathematics, things are always chaotic, and what happens is that people come along and generalize and simplify things, and eventually they get conceptually well understood. And then we teach them to the undergraduates." And he gave an example of sort of Cauchy's work trying to understand the real numbers, which at one point was sort of, the frontier of mathematics, but now we teach it to the first years. Things like Cauchy sequences and things like this. And he convinced me. And I came away thinking, it's all fine. Like mathematics might look complicated now, but if you just leave it for 100 years, it gets simpler. And it took me a long time to realize that actually is a lie, right? Class field theory was solved over 100 years ago, and we still cannot fit it into under 200 pages. Right? Class field theory is complicated. And it is not, as far as I know, there are not people working on trying to make this theory simpler. Right? But there's a lot of famous historical people involved here, a lot of brilliant ideas, and it's still, there's a quote in this book by Castles, there's a quote by Tate that says the main theorems are true because it could be no other way. Somehow it's not like you understand them, it's just you've become resigned to them or something. I don't. So that's a really big proof. But of course, it's also a very unambitious question because we're trying to understand commutative Galois groups, and commutative groups are the simplest groups, and most Galois groups are not commutative at all. So what's the correct question, really? Right. So what's the next simplest kind of group after a commutative group? And so maybe it's like a nilpotent group, solvable group, and maybe we should try and understand, what all the number fields are whose Galois group over Q is nilpotent or something like this. And it turned out these were not the right question. People were stuck. Right? These were not somehow the right questions. You couldn't find this clear. Class field theory is a very beautiful. The statements are. You have to introduce more machinery to explain what the statements are, but the statements are quite clean. And the moment you move from commutative groups to what look like the second most simple kind of groups, things get very complicated. And that was the position until the mid to late 1960s, where Langlands came along and he had the insight that he realized that the simplest kind of groups were not, after commutative groups, the simplest groups were not nilpotent or solvable groups. He observed that, in fact, the reason that Galois theory worked with commutative groups was that commutative groups, these were really the images of one-dimensional representation. We were really very complicated groups, and then looking at one-dimensional representations of those groups, and then the images, the commutative. Galois proposed that the correct generalization was to maybe look at two-dimensional groups. So there are complicated groups with faithful two-dimensional representation, right? SL2F5, the A5 tilde. This is a group of order 120. It's a non-solvable group, but it still injects into GL2 of the complexes. And there are modular forms that explain this extensions of the rationals with Galois groups like that, even though that group's quite complicated. So this is what was going on, it turned out. We look at two-dimensional representations of Galois groups, and these are related to modular forms, which are functions on GL2 of the reals. And so Langlands realized that n-dimensional Galois representations and automorphic forms for GLN should be related. And this was now the Langlands program, right? And class field theory was all of a sudden the GL1 case of the Langlands program, the trivial special case of the Langlands program. Okay, so you think class field theory is complicated, and then you look at Wiles's proof of Fermat's last theorem, which proves a fragment of the Langlands philosophy for GL2, and it needs all of the main theorems of class field theory, and also a lot of geometry and algebra and lots of other things. Right, so Wiles' proof establishes a very small fragment of the Langlands program for GL2, and this proof of Fermat's last theorem, several thousand pages long, if written out in full. Right, and that still is the case 30 years later, and that's just GL2. So you can kind of see, So actually, Wiles's proof was also had a mistake. For those of you in the room that are old as me will remember well the chaos that sort of happened. He announced this proof, and it was a big deal. Front page of the New York Times, and rumors. And news travelled less fast back then because there was no World Wide Web. There was an internet, but no World Wide Web. And it turned out there was a mistake, and then there was was it being fixed, and had faultings fixed it, and nobody knew what was going on, and everyone was working inside. It was a very strange time. And then it was fixed. And but when you get to big proofs, then maybe it's not surprising that
this isn't important, but it's certainly more than several thousand pages, depending on what you mean by in full, right?
Yeah, depending on what you mean by in full. I don't know. You think it's more than several thousand?
Where do you want to start it?
Definition of the natural numbers.
Oh, then it'll be more than several thousand.
Okay. Given that part of my job is to type this thing into a computer, it's rather scary to hear. Okay, so there's a story of how ideas turned into proofs, and then they turned into bigger proofs, and then they turned into massive proofs. And are they even if we can't even get them right, right? Are they even should humans not really be dealing with proofs that are that big? Is it? Yeah. But there's another way that proofs can get big, and this is really the topic of the topic of this of today, right? And this 50 years ago, this Apple-Harkin proof of the four-color theorem. This is the statement that every planar graph can be colored in four colors. And Apple and Harkin, what they did was this is a statement about you can't check it, you can't prove it. It's like Pythagoras. There's infinitely many right-angled triangles, so you can't prove Pythagoras' theorem by drawing all the triangles and checking it for each one. And it's just the same here. You can't prove the four-color theorem by drawing all planar graphs and then checking it for each one. But fortunately, they realized that actually, if they wanted to prove something more complicated than the four-color theorem, they could check it for finitely many graphs, and there was a chance that if there was a finite set of graphs that had several nice properties, they'd be able to deduce the four-color theorem. So they had access to a computer, which was really crucial. And they also had an algorithm for generating this set. So they had to find a large set of finite graphs that had some nice properties, and they had a heuristic argument that suggested that this finite set should exist and shouldn't be too big. And they reckoned that if their computer churned away at it, it could maybe find this set within a month. So that was what they did, and they found this finite set, and then they had to check these complex properties that each element of each graph in this set had, and so now they had to do a really gigantic computation. It was millions of, they had to do millions of computations. So this proof is also big, like the proof of class field theory is big, but it's big in a very different kind of way, right? If you wrote it if you wrote it out from the axioms of mathematics, it would be gigantic, but it would be different as well, because firstly, it was just too boring. It's boring, right? It's mechanical rather than conceptual, but it's still without a doubt big. Okay, but as far as I know, you can find humans that say they've read the proofs of class field theory or even of Fermat's last theorem. I have not read all of the proof of Fermat's last theorem. There's hard analysis in there that I've never carefully checked. But I could, in theory, read a proof of the four-color theorem, but it would just be a very, very boring thing to do. So there we go. So there's two ways that proofs can get big, right? So you have to do millions of mindless calculations. And the computer did a lot of these calculations, but not all of them. Some of them were done by Harkin's daughter did some of them, apparently, according to Terry Tao. And not all of these hand calculations were correct. They're sort of stored on microfilm, but and some of them, like a lot of the graphs were drawn by hand, and sometimes the graphs that you've got to draw 1,960 odd graphs. You're going to get kind of bored at some point. And some of the graphs, you look at it, and the dots you can't quite work out if that's one dot or two. So the original proof was kind of quite noisy. Ultimately, it turned out that the ideas were right and the proof was correct in some sense. But it really took 20 years before there was a sort of a part where by 1996, computers had got quite good. And the entire tedious part of the proof had been sort of mechanized by Robertson, Sanders, Seymour, and Thomas, who are people that are really credited in sort of convincing the world that this theorem was definitely actually proved. You could object that you could make objections to the original proof, especially the methodology, because this is somehow it's not quite mathematics, right? There's some sort of experimental part of it where you check lots of things by hand. And of course, there's another issue with this proof. Even after the 1996 version, there's still this philosophical objection. There's several objections to this proof. Like, if this proof is kind of too big for a human to understand, then is it a proof, right? Because what is a proof? What's the point of a proof? Is it just to check that a statement's true, or is it to explain to a human why? Does mathematics exist if humans don't exist, right? Or is mathematics just an idea we have in our heads? And if a human can't understand proof, then is it really a proof? I don't know. So there's a philosophical objection, and then there's this practical objection. It's like you're relying on computer programs, and you're relying on computer programs written by humans. And of course, computer programs famously contain bugs. And so do we have to, do you have to somehow read the proof, run the code, and then read the code and verify that the code actually does what it's supposed to be doing? So there's that. And of course, some people, you might not like the poor color theorem because you might think it's not the right proof or whatever. But of course, the genie's out of the bottle now. So this was just the beginning. And I don't want to tread on the toes of the next speaker, but I think we're probably going to see larger examples of computer-assisted proofs in the next talk, because computers have got a lot better. So our ambitions have got loftier. But let me just flag one example I'm fond of, and it's Hales's proof of the Kepler conjecture. So this is a sphere packing in 3 dimensions. The best way to put oranges in a box is the way that grocers have known for centuries, probably longer. So Hales managed to prove this optimal way of putting spheres into 3 space. And his proof was also computer assisted, and it involved, again, thousands of computer calculations, or tens of thousands of, ultimately checking tens of thousands of equations. You've got some funny region of R cubed defined by some polynomials, polynomial inequalities, and then you've got to check that some function is less than or equal to some other function in this entire region, and there are algorithms which will do this. You sort of check it on the sufficiently many points on the boundary, and then you argue that. So this relies on a lot of C code, and Hales proved this in 1998 and sent the proof to the Annals, and they sat on it for 7 years. And then they made some statements saying, okay, they were going to publish it, but the referees were only 99% sure that the proof was correct. Was the conclusion. And this, of course, infuriated Hales. But this paper was unique in the annals of mathematics, in which it came with this proud badge that said that the theorem might not be correct. And this is quite ironic, because this was in 2005. And let me show you 2 more Annals papers. This one's from 2004, and it's a theorem in algebraic geometry that says that all moduli spaces are quasi-projective. And then Hales is 2005, and then here's a paper from 2006 that says that not all moduli spaces are quasi-projective. And there's even a remark in the abstract that this contradicts a recent paper. It's a reference to another paper in the Annals. So there were no notes on either of these papers, even though the main theorems directly contradicted each other. And obviously either mathematics is inconsistent or one of these papers is wrong. But if you just look at the papers in the Annals, up until quite recently, there was no indication at all as to which one was true and false. And when I was having my midlife crisis in the late 2010s, I would go around proudly giving this example. I was banging on about it, encouraging people to send proofs of the Riemann hypothesis to the Annals, saying that. First you cite the first paper, then you cite the second paper, then you deduce a contradiction in mathematics, and then you deduce the Riemann hypothesis. And then the 2 references of these 2 papers. And to my delight, I discovered about 2 years ago that now one of these papers, when you click on it, it's got a big red thing across it that says retracted. But it still doesn't say it on the abstract. So you look at the abstract and I won't tell you which one it is. but you click on the PDF. Once you've clicked on the PDF, it says retracted in big red letters on the false one. So now let me tell you about computer proof checkers. These are computer programs which are quite funky. So computers have been around, lots of computer science departments were popping up in the 1970s, and they had access to computers. And these computer scientists were designing tools, and the idea of these tools is to help mathematicians to check proofs. So I'm talking about not computer algebra packages, I'm talking about interactive theorem provers. So Rock and Isabelle were 2 very early ones, and Lean is a newer one. And so these things are programming languages, and they know the axioms of maths and the rules of logic. This is variables in a normal programming language can be like numbers or strings or whatever. But you can have variables in these languages, which represent theorem statements or theorem proofs as well. And you can manipulate, you can say that A implies B. You can talk about things like this in this language. So it's like a normal programming language, but it's got extra stuff on top. And the idea is that if you can translate a mathematical proof into one of these programming languages, then you compile the proof. If the proof compiles, then that means that the proof definitely follows from the axioms of maths using only the rules of logic. And you might not see, I mean, the axioms of maths are pretty grimy, low-level things. You don't see the full details of what's going on. That's hidden from you. But this is what's going on behind the scenes. And so the clever programming languages, you have things, it sort of looks like mathematics the way a human would write it, but behind the scenes, it's frantically reducing everything to the axioms of maths, but not sort of showing you the gory, you don't want to know, as a mathematician, you don't want to be dealing with the axioms of maths. So that's how you formally verify a proof. You translate it. So when I say informal, this is a funny use of this word. So just a flag. When I say an informal proof, I just mean a normal proof written in English or a human language. When I say a formal proof, I mean a proof written in one of these programming languages. So that's what I mean by the words can be used differently by different people, but that's what I mean by formal and informal. So by the time these systems started getting good, they were being used. The computer scientists were like, great, now we've got these systems which are good. Let's use them and convince the mathematicians that we've got something wonderful. And so what proofs shall we attack? Oh, I know. Let's attack these computer-assisted proofs because there are these issues with computer-assisted proofs. What if there's a bug in the code? We can use these systems to check that there's no bug in the code. And so, the consequence is that you get Georges Gontier checking the proof of the four-color theorem in rock. And I think the big problem with work like this historically was that most mathematicians were not particularly interested in computer-assisted proofs because they already thought that they were kind of ugly and weird. And when you look at what Gontier does, it's like, okay, it used to be you used a computer in this proof, and now you're using a computer in a different way in this proof, but it's still a weird. The mathematics is still the same. The use of the computer is a bit different. What exactly have we gained? I think there's most people, they didn't really understand what had happened here. They didn't understand that. The point is that you're still writing computer programs to check something, but you're proving that the computer programs have got no bugs in a very concrete way. And there are checks, there are all kinds of ways of checking that that the system you're using doesn't have any. You can run things through different types. I don't want to get into details, but you can really, with high confidence, you can say that Gontier's work showed that this four-color theorem is sort of guaranteed to be a correct proof, but it's still a weird computer-assisted proof. And Hales, the reason I mentioned Hales was because Hales's reaction to being told in 2005 that his proof was only 99% likely to be correct was that he did just the same thing. He formalized. He spent the next 12 years with a team of people, most of whom were Vietnamese. He got funding to check his work. In a combination of two theorem provers at the time. So they announced that they've done this in like 2016 or so, and they didn't remove the note for several years. And even though, as far as I was concerned, this theorem was now far more likely to be true than any other theorem ever published in the Annals of Mathematics, because it was one of the very few that had actually been checked by a computer proof system. And it's yet still got this note on it saying this might not be true. So there we go. So there's computer-assisted proofs, the beginning of the theory. And of course, meanwhile, mathematicians that aren't using these tools are still ploughing on with their proofs. And one great example of a massive proof is classification of finite simple groups, which was announced in the mid-1980s. And sort of in some sense had major impact on the area, sort of a lot of young people then, but not the main, in some sense, one of the big questions in the theory of finite groups was answered. And I think then a lot of people decided that they weren't going to go into group theory. So that was a kind of a big deal. And the farce was that it turned out that the proof was massively incomplete. There was a paper that announced it approved a theorem, but somehow you got to the end of the paper and the theorem still hadn't been proved, and it was, you know, there was a farcically large gap, and it was 20 years before this gap was fixed, and it was but the damage had long since been done. The original proof had a gigantic gap, and now we've got this second generation proof, which is complete. But the problem with the second generation proof is they haven't finished writing it yet, and it's currently, I think, 12 volumes have been published of the second generation proof. So there's this ongoing project that was sort of led by people like Gorenstein, who since died, to write this proof down. And so the hope is it's going to be 13 or 14 volumes. And I talked to Inna Kapterbosc, and she says that they're close now. She says it won't be long. So we will actually have a complete proof of the classification theorem. But amusingly, yeah, philosophers got interested in this proof because this is really the big, in some sense, this is the big, if you don't count these funny computer-assisted proofs, this is like the biggest of the non-computer-assisted proofs. 10,000 pages plus. And yeah, a philosopher was trying to understand whether this was a proof and what a proof was. So I asked one of the authors, what are the chances are that there's going to be a mistake in these 10,000 pages, and was just told, well, obviously there'll be a mistake. And then the philosopher was like, so what exactly do you mean by proof? A funny situation. Of course, there's going to be, that's not the right question, right? The question is, will there be a problem? Yeah, will there be a serious mistake? Not will there be a slip? Yeah, of course, there'll be a slip. So there we go. So computer assistance, I've talked about these tools that can be used to check proofs. And in 2017, they were being used to check computer-assisted proofs. But because, I mean, as is probably quite clear from this talk, I've been highlighting human errors in mathematics, in my own, you know, there's not only my own subject, right? Algebraic number theory. I've been highlighting errors in algebraic number theory. And this is one of the reasons I became quite distrustful of my own. I've had it difficult to do research in my own area because the nature of the areas, it's so complex that you constantly relying on work of other people. And you know, if you suddenly realize that you don't quite believe the work of other people, and you don't have time to read it all, then, you know, like maybe these formal verification tools, they shouldn't be used to check the full color theorem. Maybe we should be using them to actually check the human big proofs. And I was arguing this since 2017, and initially I wasn't taken at all seriously, not least because the tools simply weren't good enough. Right? It was sort of completely unfeasible to do this. And as I say, but you know, I felt that there was a need, and we should work on it somehow. And I basically got a team. I basically got a team of undergraduates who didn't know any better. This was the thing. The staff thought I was crazy, but the undergraduates didn't know any better. So I trained a team of undergraduates who started building a database of undergraduate level mathematics. And things just kind of snowballed from there. So as I say, the big problem with this is that it was absolutely clear to me. I'm subscribed to the archive mailing list, and every day I was getting another email saying, here's 20 new papers in number theory comprising 200 pages of complex mathematics. And then every day my undergraduates would write another 100 lines of code. So it was clear that we were never going to catch up. And in fact, every day we were getting more and more behind. So we were fighting a losing battle. But the other thing was programming in these languages I found terrifically fun. I basically got addicted to the language. It was like you were turning mathematics into a computer game. And you know, stating the theorem is like making the level, and now you've got a puzzle game like a Sudoku, and then proving the theorem is solving the level. And you prove the theorem, you solve the level, and you get a little Tada emoji, and you get a little adrenaline buzz. And then you prove the next theorem. And then next thing you know, it's 2 o'clock in the morning. It's all what happened to me. So I didn't really care the fact that I knew that every day we were getting further behind, because as well as believing that one day mathematics could work like this, I was also basically having a lot of fun. So there we go. So it seemed like a losing battle until last month. So I spent most of the talk talking about what happened 100 years ago. So I'm going to tell you a story of something that happened last month. And it's about mythos and soul, which are fancy names. So what's mythos? So this tech company, Anthropic, a month about a month or so ago, a month and a half ago, there was this big sort of they released a blog post saying that they got an exciting new language model called Mythos, which was so good that it could hack into any computer system in the world, and it was so amazingly powerful that it could not be released to the public, and they were going to release it to some major corporations to try and so they could secure their systems before this thing got leaked. So that was the press release. That's just what tech companies do. And then a month later, they released it to the public anyway. They rebranded it. They said that Fable was Mythos, but with some extra security things bolted on. This was released as Fable, and people like me had access to this now. And then a week later, the US government pulled the plug. They said that they said they'd found a way to jailbreak the system, and it was now an incredibly dangerous piece of software that should not be in any foreign company's hands. So they banned it for being too dangerous, and it's been inaccessible ever since then until last Wednesday. And then 2 weeks ago, OpenAI, they realized that Anthropic had got a lot of positive PR from this. So 2 weeks ago, they tried the same thing. They announced that they were releasing their new model, Sol, again, because it's far too dangerous to let the regular humans have it. So they're releasing it to a select few companies, but they're going to release Sol to the general public, within the next few weeks, presumably. So I'm not interested in using this software to hack into banks. I'm interested in using this software to accelerate the program, right? To accelerate the formalization of mathematics. So Lean's an interactive theorem prover. So the question I just want to talk about in the last few minutes is how good are these dangerous language models at writing the things I care about, mathematics or the Langlands program? How good are these things at translating mathematics from human language into Lean? Because these things are very good at writing. This is one of the big selling points of these things. These things are, teenagers are falling in love with them and getting advice from them, and people are asking them for medical opinions, but a lot of people are using them to generate computer code, and they're extremely good at writing computer code now. So people in April were talking about, how AI was now just going to write all of the Lean code ever, and you didn't have to, that was it. And humans writing Lean code, we were out of business, AI was going to take over. And I came up with a challenge to prove that this was not the case. I was quite pleased with this challenge. And the Jacobian challenge, the idea was, Lean had the theory of compact Riemann surfaces, and it had the theory of compact complex Lie groups. But given one of those things, you can make another one. The Jacobian of a compact Riemann surface, named after Jacobi, who was 1800s. The Jacobian of a compact Riemann surface is a compact complex Lie group. And the challenge was to define the Jacobian of a compact Riemann surface in Lean, prove it's a compact complex Lie group, and prove basic theorems about it. For example, define the Arval Jacobi map. So Arval also, 1800s, early 1800s. Define the Arval Jacobi map from the Riemann surface to its Jacobian. And, prove it's a holomorphic map and prove various functorial properties. So this was my challenge. This is a small Lean file that says, define Jacobian of a compact Riemann surface and prove basic things about it. And so I said that, this stuff was known for 200 years. And I said that, I bet that nobody could do it, that AI was not good enough to do it. And I was dead right. People try, like somebody from Facebook got in touch with me and said they were trying it and they'd failed to do it. And there were individuals trying it and big labs as well. So nobody could define the Jacobian of a compact Riemann surface. I mean, it's not difficult to write down the definition, but and actually proving, that the lattice is actually discrete in the differentials. You've got to do some Hodge theory. There's some content here. So nobody could do it for about two months, and several groups tried. And then Fable was released in June, and 3 days later, some random software engineer just got in touch with me and said, "Oh, I've done it." Didn't know what a Jacobian was, but yet he'd still defined Jacobians, and he knew he got it right because he'd proved all the theorems right. The challenge was to define the Jacobian and then prove these theorems about it. And he proved all the his machine had proved all the theorems because they'd found a good textbook which had all the proofs in. And the textbook had been, the relevant parts of the textbook had been translated into Lean. And I thought that was great. because it meant that I was wrong, right? This area is moving so like what was true in April was no longer true in June. That's how fast. What was true in April was really, really vastly false in June. That's the other thing. I can't convey how quickly this area is moving. I'm giving this talk. Last month I would have told you about another story, and next month there'll be another story. I'm just telling you this month's story. So the unit distance conjecture is the last story I'll tell. So this was a conjecture made by Erdős in 1946 that says for n points in R squared, how do you put n points in R squared to maximize the number of pairs of points which are distance one apart? And Erdős says, well, here's one way of doing it, just put them in a square grid. And like a generic point in this grid, like the boundary, there might only be 2 or 3, but a generic point in this grid, there's 4 points that are unit distance from it. But you've got n points there, there's going to be about 4n pairs of unit distance points. So the question is, can you do better than squares? You do hexagons, but you get 6n. It's still O of n. Can you get O of... Erdős conjectured that O of n was better. You couldn't ever get O of n to the 1.01 or whatever. He could prove an upper bound of O to the n root n. So the question is, can you do better than O of n? Can you manage to get more than n pairs of points asymptotically on average close together? And this was an example of a good problem because it was very hard. And people believed it was true, and related questions have been proved. And serious people had tried to prove this, and there were partial results. And it was a problem. It wasn't just a problem that Erdős had raised. It was a problem that Erdős had raised and a lot of people had thought about. It was highlighted as one of the most important of the Erdős problems on the Erdős. There was like top 10 Erdős problems, and this was one of them. And then in May, ChatGPT solved it. And to everyone's surprise, it didn't prove it. Gowers was super excited. He was like, it's true, it's proved it. How's it done it? And it turned out it wasn't true. It disproved it. And that may be why humans hadn't done it, because they were all convinced it was true. But the reason it was false was really quite a surprising reason. Because this is a question in discrete geometry, but the proof used class field theory. And the idea is you start within the imaginary quadratic field, Q root D, and then you make this field that Hilbert conjectured existed, this Hilbert class field of that, and then you take the Hilbert class field of that, and then you take the Hilbert class field of that, and then you keep going. And like in theory, this process might stabilize. Like if you start with the rationals, the Hilbert class field of the rationals is the rationals again. But if you start with Q root minus D, and D is very, very big, it turns out that this sequence of Hilbert class fields goes on forever. And so what you do is you take these very complex number fields, you embed them in the complexes, you look at certain finite subsets of the rings of integers, and this gives you a counterexample to this conjecture of Erdős. And so now all we've got to do is we've got to guarantee that these Hilbert class field things, these Hilbert class field towers can go on forever. And this is a deep result of Gollard and Shafarevich from the 1960s. And the proof makes heavy, extensive use of class field theory. So these 200 pages of mathematics. So this is great, right? This is great because this is showing that number theory has got some application in discrete geometry, which is very surprising. And this is a question that was of interest to humans, and humans couldn't do it, and then an AI language model has done it. So that's what's coming. Okay, that's what's happened in May. And of course, there was some press interest because like AI had finally solved a hard mathematical problem that humans couldn't do, right? This is the first example, and I'm sure they're going to be more soon. But that's what happened, and then the press coverage died down, and that's kind of, for a lot of people, that was the end of the story. But let me tell you the epilogue. So 1 week after the announcement of this AI, the question, the AI has written a bunch of rubbish. AI has written a bunch of stuff. How do you know it's right? Because AI will lie to you. You tell it to do something, it'll say, "Oh yeah, I've done it," because that's what it wants you to, you want to hear that. That's what it says it's done. You do have to check that this proof is correct. But several mathematicians were prepared to stand up and say they've checked the proof. But the tech company Logical Intelligence, they announced within a week that they'd completely auto-formalized this thing. They'd translated this 20-page paper into Lean, and they'd got a formal proof that the Gollard-Shafarevich theorem, this deep result using a lot of class field theory, implies that Erdős unit distance conjecture is false. So the actual content of the AI generated stuff has been completely checked by Lean. And then all of this, the translation was done by a machine. And you kind of thought that was going to be the end of it. But then last week, to my genuine surprise, Boris Alexeyev, an employee of OpenAI, but doing this evenings and weekends, he went one better and he completely formalized the entire thing. And in particular, when I heard that this had been done, I thought, can that really be true? Because that must mean that a machine has just proved these 200 pages of class field theory that I knew was just completely inaccessible, a major multi-year project. So I was very surprised, because, as I say, this means that it must have auto-formalized at least sort of 3/4 of the main theorems of class field theory. And there was very little of this material was in Lean's maths library. And so I had a look, and that was exactly what had happened. And so I checked that the AI generated code really does contain proofs of the more difficult of the two main equalities of global class field theory. I have on this very laptop, I have compiling computer code that proves this thing here, something which, if you'd asked me 1 week ago, I would have confidently said was like at least a year away. So this was all done by machine. So that's great, right? For me, that's a step change. Okay. So like, if somebody who's not a professional mathematician can just upload a book containing the main theories of class field theory to, the Sol language model, and can just press a button, and a month later, the whole thing's been translated and checked, then, what else can we do? And in particular, what can we do in a year's time? Right, because currently Lean's maths library is 2.25 million lines of code, and we're hugely proud of this. It's got most of an undergraduate degree, and it's got a bit of graduate level, some difficult commutative algebra, some difficult algebraic geometry, some difficult category theory. But I think that all this that I've spent 9 years of my life working on, together with a bunch of undergraduates and people around the world, I think within a year or two, we're just going to have many standard graduate textbooks are all just going to be completely translated into Lean by machine. And there will be AI generated libraries, which will be more like 2.25 billion lines of code. Like something really surprising is going to happen, and it's going to happen very, very quickly. So that's it, right? I started working in this area because I was convinced the mathematicians weren't as smart as we think we are. In this talk, I've highlighted several errors and omissions in the mathematical literature. And I do wonder whether now auto-formalization is happening, what's going to happen when we really get going, right? In a few years' time, I wonder whether we're actually going to go backwards, and we're actually going to know less about the Langdon's program than we do now, because the papers that we thought were right but turned out to be wrong will have been uncovered by machines. And so now we're going to have the tool which I wanted. This thing, you type in the LaTeX and you get a red underline, and the red underline means you've made a mistake. Right? That was science fiction 5 years ago. In 5 years' time, that might be something we're all using. It's really got to that point now, right? So I'm also very unclear about who's going to be owning that tool. Is it going to be some free and open source? Am I going to win with my free and open source maths library, or are the tech companies going to win? And if the tech companies going to win, then how much are they going to charge the universities, and how much are they going to charge the journals? Right? Is it all going to be free and open source and you can download it? Or is it going to be powered by these models, these tech companies? And will it become something that no mathematician can do without? So mathematics will become more accurate, I think. Yeah, but what's it going to cost us? Okay, thank you very much.
Time for a couple of quick questions, and probably more importantly, a couple of quick answers.
So I'm okay. I don't know anything about Lean really, but my understanding is that you can trick it into saying something that looks like a code.
Yeah.
Okay. My understanding also is that AI generated Lean code is very verbose. It goes on for ages.
Yeah.
It's hard to make sense.
Yeah.
So how does one avoid the 2.25 billion lines of code containing like a contradiction?
Yeah, it can be done. There's a trick. You actually look at you actually look at the proof, and then you run it through an independent type checker. And you say, is this actually a proof of this? It's like a factory. If I've got a dodgy computer program that says, I factored this large number, it's this times this, you don't have to worry about this. You take the two factors, you multiply them together again. You see if you get the thing you started with. So there are tools that do things like that.
Going back to your last question, how much have you spent on Fable in the last few days?
Me personally, 30 quid.
Young, did you have a question? Yeah.
My question is a little bit,
Oh, no, Imperial. Yeah, personally none. But Imperial has spent 30 quid on my behalf. I mean, it spends $200 a month on Fable for me.
Yeah.
sorry, this is a slightly long question, but I'm going to presume the prerogative of a host today.
Yeah.
But you, anything.
Sure. So, we had this discussion about whether or not lean gives certainty.
Mhm.
So certainty, and some people believe this, right? And I don't quite believe this. I'm more skeptical. But I thought it's boring to have philosophical discussions about certainty.
Mhm.
I thought I'd contribute something constructive and see if you agree.
Okay.
So it's sort of similar to Church's thesis about computation, right? So
Uh-huh.
people don't have an independent definition of computation, but you hypothesize that anything we believe to be computation can be implemented on the Turing machine.
Mhm.
So you take that kind of thing. Now let's take the assertion, any proof checked by lean will always be correct.
Mhm.
I'm going to call this Buzzard's thesis.
Okay, great. Yeah, I'll happily
Are you
make
happy
that.
with it?
Yeah,
Okay, good. Yeah, I just wanted to check whether you're happy with it.
because there are tools,
No.
tricks.
So we don't have to discuss this anymore because this is a thesis, right?
Well, I think it's a theorem. No. Okay, yeah, I'm happy for that to be Buzzard's thesis.
Okay, good.
But I can give you technical. I mean, I've already not given.
No, I understand what you're saying, but to my mind,
For me, this is this is the definition of correct.
no, I think it's great. Whatever you're doing is great, but I still think it's a question of probabilities.
Ah, yeah, okay.
Okay, we'll finish with a question from the I&I director. That's a good place to finish.
Big shot.
Before the cups of tea and coffee, yes.
So I remember you giving a talk, of course, at I9 just a few months ago, and commenting in some sense also on the was it mass inc proof of in lean of the
Yeah. 8D sphere packing.
million lean lines of lean code,
Yeah.
and I think you weren't too impressed, and I think. You can now contradict me. And maybe it's not a Kevin theorem. Mainly because it was not giving insights, while
Yeah.
was
Just literally translated.
was to give more structured proof.
Well, I had a different hat on.
Okay.
And now I'm arguing a different position. But yeah, I'm
So at the moment,
I'm just giving
this is
contradictory.
the same category of just loads of slow.
I think we're just going to check the textbooks, then we're going to check the papers. Yeah, this isn't about doing new mathematics. This is just about.
No, but I mean, it's about. I thought
It might give us.
there to explain mathematics.
No, but no, it's not going to explain anything here. It's just going to say actually that bit's wrong, which is different, right? It's going to unexplain it. It's going to say, oh yeah, it says that this is obvious, but actually it's not obvious. But this isn't about.
This is checking something.
But like the thing about work of Fields medalists is that humans check it quite carefully because they're going to have egg on their faces if they give out the Fields medal to someone whose theorem turns out to be wrong, right? But the thing about 99% of mathematics is it doesn't get a Fields medal. So, let's check that next.
Yeah, I think that's a nice place to stop. So before we head for coffee and tea, it just remains to thank Kevin for a fantastic and wonderful talk. Thank you very much.